So, we have already discussed what LP space is, and if a signal belongs to the LP space, then how can we calculate the LP norm of the signal? So, today we'll see some examples, and then we'll see that certain commonly occurring signals will not lie in certain LP spaces, and hence we'll discuss of LP extended spaces. Okay, so let's take example of this. Suppose f of t is tan hyperbolic of t for t in the interval 0 to 5, and 0 in the when t is not in the interval 0 to 5. Okay, so suppose this is it, and we want to see if f belongs to the L1 space, where f and that maps 0 to infinity to r. Okay, so we want to check this. So to check this, what we need to do is we need to first see whether holds or not. So we have to check whether f norm of f is integrable or not. Okay, absolutely integrable or not. Now here, for simplicity, we'll choose p to be equal to 1. So we are taking a 1 norm. Okay, so 0 to infinity norm of f of t dt is 0 to 5 norm of f of t dt. This is nothing but 0 to 5 tan h t dt, which is log cos h of t evaluated over the endpoints 0 to 5. This gives me log cos hyperbolic of 5. Okay, log cos hyperbolic of 0 is 0. Cos hyperbolic of 0 is 1, and log of 1 is 0. And this is clearly less than infinity. Okay, which means that the signal f that has been given to me is essentially in the L1 space. Okay, now what is the L1 norm of this particular signal? This is going to be the same as we had evaluated here, with p to be equal to 1. So this is what will be the L1 norm, and as we have evaluated, it turns out to be log cos hyperbolic of 5. This is the L1 norm. Similarly, let us take a signal f of t. F of t is sine of t. Okay, for t between 0 to infinity and 0 for t in the interval this. Okay, so we are considering a signal which occurs from t equal to 0 onwards. Okay, now will f belong to the LP space for. Okay, I'll be dropping out this particular term henceforth, because the moment we say what is the, I'll be dropping this term in the bracket, which is saying the domain and the range of f, because when we define it, it becomes clear. So the LP space would be only for, when we check, it will be for those signals. Okay, now let's see if, so we want to see whether this holds or not when p belongs to 1 to infinity excluding 1. Okay, will any of it hold or not? And also we would check whether this holds or not. Okay, now So to check the first part, whether this is true or not for p in the range 1 to infinity, we need to check whether for some q norm of the instantaneous value of f raised to the power p, whether this will hold or not. Okay. Now in this case is what, if we check, so 0 to infinity norm of f of t qp dt is nothing but 0 to infinity mod of sine t to the power p dt. Okay, so this is what you get. Now if you look at the sine curve, how does it look? Roughly the sine curve is going to look as this, right, as it progresses. So how would mod sine t look like? Mod sine of t is going to look like this blue curves. I'll draw it again. So the positive part remains positive, the negative part comes up, right? And then you are raising it to the power p, so accordingly the power p will basically change the value of uh, sine t. Okay, for some value of p between 0 to 1, what you see is the integration essentially tells you the total area under the curve over the length 0 to infinity, right? So now if p is between 0 to 1 to infinity, what happens is the area under the total area under the curve would be not less than infinity. So this integration is not defined. Okay, the integration does not exist. So f does not belong to any LP space in the interval 1 to infinity. But what is the max of norm of f of t with some q for t in the range 0 to infinity? This is same as asking what is the max that you will have over the interval 0 to infinity or the mod of sine of t. And this is what? This is going to be 1, which is less than infinity. So this indicates that the function f that we're talking of, the sine function, is in the L infinity space. Okay, so f does not belong to any LP space when p is not infinity, but it belongs to the L infinity space. Okay, similarly you can verify for mm, signals like cos t, tan hyperbolic t, tan inverse t. Okay, that these signals will belong to L infinity but do not belong to any other LP. Okay, or p belonging to 1 to infinity, infinity excluded, of course. Now what about signals which are defined as, let's say, this e power t over the interval 0 to infinity? Okay, and at 0 for t in the interval minus infinity to 0. That's so. Now what happens here? Will f belong to LP for p in the range of 1 to infinity? Will f be in the L infinity space? What can we say about this? Now, again, to check for f belonging to LP space, you need to evaluate the integrability, the Q integrability, right? So P integrability, sorry. This dt has to be less than infinity, so we need to check this. Okay. Now, from the nature of the exponential curve, you know that as t progresses, the value of e keeps on increasing, which means that in this particular case, this um, integration does not exist, right? This does not exist, which means f does not belong to a LP space where p is something from 1 to infinity. Now, what about f being in the L infinite space? Well, to answer that, just look into this. Can you find a finite value for this? Whether the maximum or the, I should not say maximum, I should say actually supremum, okay, or essential supremum. In this case, essential supremum for this function is same as the supremum of the function, okay. So, in the previous part, I think I can correct this to this. Okay, so let's go back to this case. So here, will this be less than infinity? And the answer is no, because exponential of t is a ever growing signal, right? So doesn't belong to even the L infinity space. So f doesn't belong to the L infinity space. So this is a signal which does not belong anywhere. Let's take another example. F of t is equal to e power minus t for t in the interval 0 to infinity and is 0 for t less than 0. This is what it is. Again, we raise the same questions, that whether f belongs to the LP space 1 to infinity and whether f belongs to the L infinity space. So let's see this. So what? So 0 to infinity norm of f of t, some q norm of f of t raised to the power p dt is nothing but 0 to infinity e power minus pt dt. Okay, and I think you can verify this to be less than infinity. Okay, so the area under this curve is going to be finite over the interval 0 to infinity, right? So once you verify this, you can actually establish that f belongs to LP. In fact, it belongs to all the LP spaces. Now, also, if you evaluate the essential supremum of this f over the interval given, then it turns out that this is going to be 1, which is again less than infinity, thus indicating that f belongs to the L infinity space as well. Okay. Now I have just given you conditions for whether I belongs to LP space or L infinity space or not. Once it belongs to LP or L infinity space, you can you can calculate the LP norm or the L infinity norm. Well, the L infinity norm is directly the essential supremum that you are calculating. For LP norm, whatever value you have evaluated, that has to be raised to the power 1 by p. So, if to reiterate, if f belongs to LP for p in the range of 1 to infinity, then the LP norm is 0 to infinity, assuming the time interval is from 0 to infinity under consideration. Norm of f of t, which norm? The q norm, and this is the q norm that you have to fix. P gets fixed because of LP dt, and this is raised to the power 1 by p. So this is the LP norm. And if f belongs to L infinity, then the L infinite norm is the essential supremum over the time interval 0 to infinity for norm of f of t, q norm of f of t. Okay, so this is how you can calculate the LP norm and L infinite norm. Please remember that the value of the LP norm or the L infinity norm changes with the choice of q. If the q is different, the value will also change. Okay, now from these examples, what we saw is that um, the sine function, the cos function, tan hyperbolic functions, they are uh, the tan inverse function over the interval 0 to infinity do not belong to the, I should rather say, the LP space, where p is not infinity but a finite number. So these all belong to the L infinity space, but not to the LP space. Okay, they do not belong to the LP space. And these are commonly occurring signals. In fact, e power t also, it doesn't belong to any space, even not to the infinite space, right? I include infinity here. Doesn't belong to even the infinity space. But we want, so we need to understand, or we need to have something that includes these signals in such spaces. So what we do is we will relax the definition of such spaces, and what we get, we'll call them as extended spaces. Okay, so this is where we come to something known as the LP extended spaces, which are also represented as LPE spaces. Okay, so signals which are in LPE space need not belong to the LP space. So we'll see what LPE space is. Okay, so a signal belonging to LP will definitely belong to its extended space, but the reverse implication does not hold. Okay, so what is this LP extended space? So to understand this, let us again revisit those signals which were not, let's say, in the L2 space. Okay, for example, the sine. The sine function is not in the L2 space, right? It is not in the L2 space. So what if, instead of looking into the sine signal over the entire interval 0 to infinity, we look into the signal over smaller intervals starting from 0. Okay, so let's say that f tau of t, so um, It says that f of t is sine t. Okay, for t greater than equal to 0 and is 0 for t less than 0. This is what we are considering. Now let's say that f, we have another signal f tau of t, which is defined as sine t over the interval t to tau and is 0 for t greater than tau. So f tau of t is nothing but a truncated version of f of t, which is truncated at tau. Okay, so your f tau of t is a truncated version of f of t truncated version of f of t, that is f of t is truncated at t equal to tau. This is what we have. Okay, now f of t, f does not belong to L2. That is what we have seen. Question is, will f tau belong to L2? Okay, this is a question that we want to answer. If you see, for f tau to belong to L2, we need to check whether in 0 to infinity, the norm of f tau of t, some norm, let's say we'll take one norm for simplicity, raised to the power 2 dt, this has to be less than infinity. So this is essentially 0 to tau sine square t dt. Why? Because from tau to infinity, f of tau is defined to be 0. Is what it is. Okay, now over this finite interval, the integration of sine square t dt, the area under the sine square t curve, is going to be finite over the finite time interval. So of course this is going to be less than infinity. If this is the case, then this implies that f of tau belongs to L2. So the original signal was not in L2, but if the signal is truncated over truncated to remain over a finite interval, then the truncated signal is in L2. Okay. Similarly, what you can check is that for f of t equal to cos t, if, okay, I forgot to mention that this tau is a finite quantity, okay, in the interval 0 to infinity. So this is cos t for this, and the 0 when t is greater than tau, right? So this is what, and tau is some value that is again a finite quantity. So here also f does not belong to L2, but f of tau belongs to L2. Okay. Now, and of course, please note that when you're talking of these signals, we are not talking of whether the signal is continuous or discontinuous or not. We're just talking of some signals that exist. Okay. So this is what we have. Okay, similarly you can check for some other signals which do not belong to L2 but their truncated version belongs to L2. Now where is this all discussion going? Okay, so if you are given with a signal, let's say f, okay, if you are given with a signal f, so given a signal f says that f maps from 0 to infinity to Rn, let f tau be this with f tau of t is equal to f of t for t in the interval 0 to tau and is 0 for t greater than tau for some tau in the interval, some finite tau. Okay, this. So if tau is this, if f tau belongs to LP, if it belongs to the LP space for all tau that you can think of. So for all possible such truncations that you can have for the signal f, all the truncations if they belong to the LP space. Okay. So you choose tau equal to 2, you choose tau equal to 3, you choose tau equal to 4, you choose tau equal to 5.5, you choose tau equal to 6.97, and you keep on choosing tau. So look for all possible truncations that you can have for the signal f that has been given to you. If all the possible truncations f taus belong to the LP space, then f is said to be a signal that is in the LP extended space. And in this case, since we are talking of the time interval 0 to infinity, we are talking of a extended LP space for 0 to infinity Rn. Okay. So here your sine belongs to the L2 extended space. Cos belongs to the L2 extended space. E power t belongs to L infinity extended space. E power t also belongs to LP extended space. Okay, L2E extended space, I'll say. You have to verify whether these signals in general belong to LP extended spaces, LP spaces or not. Okay, for P being 1 till infinity. So just verify whether this is true or not. So this is what is the definition of the LP extended space. LP extended space is a collection of those signals which are such that all their truncated versions, all the possible truncated versions of the signals will be lying in the LP space. So LP extended space is a collection of all the signals whose all possible truncated versions. Of course, when I say truncated, please remember that I am talking of a truncated version whose interval starts from 0. Okay, whose all possible truncated versions are in the LP space. Okay, now please remember that even if a signal belongs to a LPE space, it doesn't mean that you can evaluate its LP now. Okay, f belonging to LPE space does not mean that the LP norm exists. Okay, so this is not necessarily true because f is in LPE. For the LP norm to exist, f has to be in LP space, not in LPE space. Okay, so any signal also, I think I told this before, any signal in LP space also lies in the LP extended space. Okay, so LP spaces are subsets of LPE spaces, but the reverse implication is not true. Signals in LP space need not lie in the LP space. Okay, so this is what is the notion of the LP extended space, and this helps us in including a lot more signals uh, in this particular definition of LP spaces. So, what I would say is we have some standard test signals, right? So, we have step signal, which is usually denoted as 1t. We have impulse, we have ramp, unit ramp, of course. So, this is t1t. You have sine t1t, have cos t1t, and you have t square 1t. Okay, where of course 1t, the unit step signal, is defined as 1 for t greater than equal to 0, is 0 for t less than 0. What you have to find out is which of these signals belong to L1, L2, L infinity, L1 extended, L2 extended, and L infinity extended spaces. This is what you have to find out. So take this as an assignment and try to solve for this and justify why would one belong to L1 but not in L extended, or rather why one would belong to L extended and not in the LP space. Okay, so we'll stop this lecture here, and we'll continue this discussion as with regards to systems under consideration. That will give us an idea of a stability or relationship between stability of input and output uh, in the forthcoming lectures. So we'll stop here. Thank you.